Okay, so we have quiz number 7 here, and for numbers 1 and 2, what I'm going to do here is I'm going to sort of walk through the steps, and I'm going to show you what I did, but I'm not going to take the time to write it out so we can sort of streamline it because we've seen problems like 1 and 2 on previous assignments from discussion. So if you want to see how to do these in complete detail, you can see reference my previous videos on problems like this. So to start off, for number 1, we have this reaction where we've seen this before actually. We got hydrogen and nitrogen gases combining to make ammonia. And we've got known amounts of each of our reactants. And so what we're asked to determine is the number of grams of basically excess reactant that'll be left over at the end of the reaction. So in order to determine what our excess reactant is, we need to first figure out what our limiting reactant is, because that's going to determine how much of the excess reactant we consume. So let's take a look at that. So here we've got finding the limiting reactant. And you are hopefully familiar with this process at this point where we take a look at each of the reactants. So here we've got hydrogen, and we took the number of moles of hydrogen we had, multiplied it by the mole-to-mole ratio from the equation, and obtained the number of moles of ammonia we would produce with this many moles of hydrogen. And then we did the same thing for nitrogen. We got 3.44 moles of nitrogen multiplied by the mole-to-mole ratio from the equation. We found that with 3.44 moles of nitrogen, we make 6.88 moles of ammonia. And so from this clearly we can glean that the limiting reactant is indeed the hydrogen. Okay, so moving on now. We're going to figure out next how to, we want to figure out how much product is made. So we know that hydrogen is our limiting reactant, and we also know that when we ran out of hydrogen, we made 0.92 moles of ammonia, right? So then the next step is going to be to determine how much excess reactant was consumed. So we know how much product we made. And then we can return to the balanced chemical equation and convert from moles of ammonia into moles of nitrogen. So we saw from the balanced equation that we can take the number of moles of ammonia that we produced and use this 1 mole of nitrogen to 2 moles of ammonia mole-to-mole ratio to tell us how many moles of ammonia, or excuse me, moles of nitrogen that were consumed. So basically what I'm saying here is I'm saying that I consume 1 mole of nitrogen for every 2 moles of ammonia that are produced. So if I produced 0.92 moles of ammonia, I'm going to consume only half as many moles of the nitrogen. So I consumed 0.46 moles of the nitrogen. And then the last step is going to be to determine how much excess reactant, that's the nitrogen, is left over. So we've determined how much we used. And we also know from the problem here that we started out with 3.44 moles. So we just subtract from what we started with the amount we used, and we're left with whatever we have left over. This is the 2.98 moles of nitrogen we see here. And if we just take that and use the molar mass of N2, we would find that that corresponds to 83.3 grams of nitrogen. And that gives us the answer C. So the right answer for number 1 is C, 83.3 grams of nitrogen. Number 2 is a kind of problem that we've seen in the past as well, where we're being asked to determine what the mass percent composition of acetaminophen is. So we're given the chemical formula for acetaminophen. It's C8H9NO2. And I went ahead of time and calculated the molecular weight for acetaminophen, and it's 151.164 grams per mole. So what I'm going to do here is I'm going to take a look at one of the elements, and carbon seems convenient because it's the first one in the formula, so I'll just do carbon. And I know from the formula that I've got 8 moles of carbon in a mole of acetaminophen, and each mole of carbon weighs 12.011 grams. And I know that a mole of the molecule weighs 151.164 grams. And so what I can do here is just make sure all of my units cancel. So moles of carbon canceled. And now moles of acetaminophen cancel. So what I'm left with here is grams of carbon per grams of acetaminophen. So by saying percent composition, what I'm basically asking is how much of the mass of acetaminophen is made up of carbon. And here, if I see grams of carbon per grams of acetaminophen, I can identify that I'm going to get a percentage out of this. And that's exactly what I do here. I just go 8 times 12.011 and divide it by the molar mass of acetaminophen, and this is the number that I get. So that corresponds to 63.5% of carbon. So what I'm saying here is that 63.5% of the mass of this molecule is made up of carbon. Okay, so if I had 100 grams of this molecule, 63.5 grams of that would be pure carbon. This pretty much already gives us the answer. The answer for number 2 is C. The reason we didn't need to go any further is because C was the only answer that had 63.5% carbon in it. So once you determined this for carbon, you could eliminate all the other answers and just go ahead and circle C, and you would be all good to go. All right, so C is the right answer for number 2. Okay, so man, that was really fast. But we're going to take it a little bit slower here for number 3. For this one, we have this reaction here, and that's given to us in the problem. And we've got masses of each of our reactants, and we're asked to determine what our percent yield is. And so in order to do that, we're also given the actual yield of the product that we're interested in. So I went ahead and calculated the number of moles for each of the reactants so that we can then quickly proceed to finding what the limiting reactant is. So that's going to be our first step. It's always the first step for a problem like this because we need to figure out how much product we make, and that's determined by which of the reactants we run out of first. So that's the reactant that's going to limit the reaction. So let's go ahead and do that. Let's take a look at this compound here. So I have 0.00824 moles of it. And from the balanced chemical equation, we learned that 1 mole of this reactant produces 1 mole of this product. Alright, and my moles here cancel, and I'm left now with moles of the product. And oh, this is great. I love this kind of mental math. This is just for me. There we go. So we make 0.002824 moles of our product. Okay, let's jump over to ammonia and see what ammonia yields. So for ammonia, we have 0.0945 moles of it. All right, and again, from the balanced chemical equation, we see that we need to consume 2 moles of it. And so when we consume 2 moles of it, 1 mole of our product is made. So 1 mole of our product is made when 2 moles of ammonia are consumed. Okay, moles of ammonia cancel, and once again we are in moles of our product. And what this gives us is 0.04725 moles of our product. Okay, so I'm going to leave the question up to you now. Which one of these, is it this one or this one, which one of these reactants is our limiting reactant? So the answer is that it's this one. This one here is our limiting reactant. And the reason why is because we ran out of it first. It limited how much product we made before this one did. So we find that this here is our limiting reactant. Okay, so the next step for us is then to just say, okay, well, we know from this right here, we know how much product we made. That's why I like this method, is because we know how much product we made. So I can just go like this, 0.00824 moles of our product. And I can figure out the number of grams of product we made. And that's going to be important because we need to figure out our percent yield, and we need to have grams of product for that. So a mole of this compound weighs 300.046 grams. And I'm not going to write it out again, but you will know that I'm referring here to the product. So the moles cancel, and I'm left with grams of our product. And so if I do that on my calculator, I would find that I end up with 3.421 grams. Oh, excuse me, I entered in the incorrect numbers. This is not 3.421. This becomes 2.472. Okay, so that is the number of grams of product that we produce. Now let me remind you that the equation for percent yield is the actual mass that we produced when we went into the laboratory and did this experiment versus the theoretical yield that we could have produced if the reaction had been absolutely perfect and everything had reacted completely. So by calculating the percent yield, what this number signifies is how much of the theoretical mass did I recover in the experiment. And of course, typically, the higher the yield, the better the experiment. So my actual here from the problem was 2.08 grams. And then the theoretical yield, the perfect yield, was 2.47 grams. And now if I just plug this into my calculator, I would discover that my percent yield is 84.2%. And that corresponds to C. So the correct answer for number 3 is C. Number 4 asks us, based on the information in question 3, which is the limiting reagent in this reaction? Well, first of all, I like to be really specific and ask what is the limiting reactant, but what you'll find is that you can sometimes use those terms interchangeably. But in any case, this is something that's really nice about this method here that I really like. What we did here is that when we found what the limiting reactant was, we concluded that it was this one. That was the process that we took for determining how much product we made. So when we did number 3 and we figured out how much product we made, we already figured out what the limiting reactant was. Those two steps sort of came together. So number 4 comes very quickly. If you had done it this way, you would find that number 4 is this molecule. Well, of course, we had that from above, and that corresponds to A. So the answer for number 4 is A. In number 5, we have a combustion reaction where we're taking toluene and combusting it to make CO2 and water, of course, and we are given known amounts of the CO2 and the water. And we're given milligrams. I went ahead and converted them into grams. And then I also took the next step and converted each of these into moles. So these are just the grams divided by the molecular masses for each of these molecules. So the key thing about this particular reaction is that we're going to suppose that toluene is a hydrocarbon. And the key thing to a hydrocarbon is that it contains only carbon and hydrogen. So that's what we're going to use as our premise for doing this problem, is that it contains only carbon and hydrogen. So if we calculate how much carbon we have over here in the products, then we can relate that completely to the amount of carbon that was originally in the molecule, because the only place that carbon could have come from was from our hydrocarbon analyte. And this is just due to the conservation of mass. So same thing for hydrogen. When we calculate the amount of hydrogen that we got in the products, we know that the same amount of hydrogen had to be from the reactants, and the only reactant that had hydrogen was the toluene. And so when we find out how much hydrogen we had in the products, we automatically know how much hydrogen was in the reactant. So let's go ahead and do this. Now that we have moles of each of our products, we can just go ahead and use those. Where if I have 0.00346 moles of CO2, and I want to figure out how many moles of carbon, just pure carbon, I have in there, I look at the chemical formula and I say, oh, okay, well, I got one carbon in there for every molecule of CO2. So a mole of, basically a mole of CO2 molecules is going to have a mole of carbon in it. Now our moles of CO2 are going to cancel, and I'm left in moles of carbon. All right, I can do this. This is good. I'm comfortable with this kind of mental math. So I have 0.0046 moles of elemental carbon. Okay. So I'm just going to remind you now that since we know the moles of carbon in our products, that's the amount of carbon that was in our reactant. And the only reactant that had the carbon was the toluene, so we know that had to have come from the toluene. That's how these problems work. So let's do the same thing for the hydrogen. So this was for carbon, now we're going to do the same thing for hydrogen. And let me move this up a little bit. So for hydrogen here, we can't just start with hydrogen, we have to start with water, and we then also have to recognize that 0.00198 moles of water are going to have twice as many moles of elemental hydrogen. So for every 1 mole of water, I'm going to have 2 moles of hydrogen. Okay, so this was something that a few people found a little bit confusing, and I just wanted to clear this up by saying, let's think of an example here. I'm going to set this up as a little side. That suppose I have 3 water molecules just floating around. I have 3 water molecules here, so I have 3 water molecules. How many hydrogens do I have? I have a total of 1, 2, 3, 4, 5, 6 hydrogens. Okay, so I have a total of 6 hydrogens in this sample of 3 water molecules. Okay, so the reason that I can say that I have 2 moles of hydrogen in a mole of water is because now, suppose I said I had a mole of water. How many hydrogen atoms do I have? I have exactly twice as many hydrogen atoms, because for every water molecule I have 2 hydrogen atoms. So the same with what we saw when we had 3 water molecules, we can now extend this out to a mole. Say I had a mole of water molecules, that would mean I had 2 moles of hydrogen atoms. Okay, so I hope that isn't too confusing. It really is just as simple as that. So I'm going to take this and, oh no, I got to do it with my calculator. I really am really bad at mental math. We were trying to do a problem in one of my graduate classes, and we had to do something like 57 minus 29. I just about, busted out my calculator. I couldn't do it. Actually, what I did was I waited for someone else to answer the question, then I just wrote it down. I am a good student. Okay, Anyway, so here I have now the number of moles of carbon, and I have the number of moles of hydrogen that I have from my products. Okay, so moles of carbon and moles of hydrogen. Okay, so what do we do with these numbers? Well, let me bring you back to the chemical equation. We now know how much elemental carbon we produced in the products, and we know the amount of elemental hydrogen that was produced in the products. And since the only place that the carbon and the hydrogen could come from is the toluene, we can suggest that these two numbers of moles, so 0.00346 moles of carbon and 0.00396 moles of hydrogen, can make up the empirical formula for our hydrocarbon analyte. So we're going to use those two quantities to make our empirical formula. Empirical formula. Okay. So I have carbon and I have hydrogen. That's the definition of a hydrocarbon, right? And I had 0.00346 moles of carbon and 0.00396 moles of hydrogen. So when we're trying to do an empirical formula, you got to remember that everything has to be in whole number values, so integers, right? Because it doesn't make sense to say say I had one molecule of this hydrocarbon, it doesn't make sense to say I have 0.00346 atoms of carbon. It just doesn't make sense. Whereas if you have whole numbers there, then you can say I have like 7 carbons in a molecule of this hydrocarbon. That makes a lot more sense. So we got to figure out how to get this into integers, and the way that that's done is by dividing both of these numbers by the lowest of the numbers, the least of the numbers. Okay, so the carbon had the lowest number, so what that's going to do is that's going to give carbon a coefficient of 1, and then the hydrogen is going to have a coefficient of 1.144. Don't worry, I didn't do that in my head. I did that on a separate sheet of paper here. So I'm not at the integer stage. So I have to take this and figure out how to get it into the integer stage, where both the numbers for the carbon and the hydrogen are whole numbers. And I could play around. I could try 2, multiplying both of these by 2. That's not going to get me anywhere. I could try 3, I could try 4, and I could keep going until I got something that was really, 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 really close to a number I could round. And that happened when I multiplied this molecule's coefficients by 7. So when I did that, carbon, of course, becomes 7, and then the hydrogen, let me just demonstrate this by calculating it. 7 times 1.144 gives me 8.008. Okay, and that's a number that I can say is close enough to 8 to where I can round it. So I'm just going to drop the extra decimals. I'm going to round down to 8. So C7H8 is going to be the empirical formula for this molecule. And that agrees with one of the answers. In fact, that agrees with D. So the D here is the correct answer for number 5. Number 6 gives us a solution of nitric acid and asks us to determine the number of moles of nitric acid, that's HNO3, that there are in 35 milliliters of 1.2 molar nitric acid. So just to preface this, let me remind you what molarity is. So the definition of molarity is moles of solute per liter of solution. So anytime you see the big M like that, that's going to be molar, and molarity is defined as the moles of your solute divided by the liter, or the volume of the solution being per liter of solution. So if I were to relate this to this problem, here I have a solution of 1.2 molar nitric acid. So what I'm stating with that is I have 1.2 moles of nitric acid per liter of solution. Okay, so when I have a liter, I have 1.2 moles of nitric acid. Great, except I don't have a liter of nitric acid. I only have 35 milliliters. So if I were to figure out some way to calculate the number of liters I have, then I could very easily figure out the moles I have just by using the molarity. So I would hope that, that you remember the unit conversion from milliliters into liters. So if I have 35.0 milliliters, then converting that to liters, I find that I have 0.0350 liters of solution. Of course, our milliliters here cancel, and I'm left with liters. Okay, so that's the volume of the solution that I have, and let's see here. If I want to figure out the number of moles of nitric acid that I have, then I need to say, okay, well, a liter has 1.2 moles, but I only have 0.035 liters. So, how many moles of solute do I actually have? And the way I can do that is, the way I can determine that is by saying, okay, well, I know that 1 liter contains 1.2 moles of nitric acid. Okay, but I only have 0.035 liters of solution. So my liters here are going to cancel, and lo and behold, I am left with units of moles of nitric acid. So if I were to just run this through my calculator, I would find that 1.2 times 0.035 gives me 0.0420 moles of nitric acid. So that would be A, and A is indeed the correct answer. So number 7 is kind of interesting. Here I'm given a 0.5 molar solution of barium chloride, and I need to figure out how many milliliters of this solution will give me 15 grams of barium chloride. So I kind of look at this and I go, well, grams and molarity, they don't really relate very well. So maybe I need to convert the grams into moles, and then I can relate moles to molarity because there's moles in molarity. So let's go ahead and start off with that and get this into moles. And that will make everything a lot easier. So we got 15 grams of barium chloride, and then for every 1 mole of barium chloride, it weighs 208.23 grams. So my grams here are going to cancel, and I will be left in moles of barium chloride. So that's perfect. Let me plug that into my calculator here, and I'm going to get 0.072 moles of barium chloride. Okay, so that's the number of moles of barium chloride I have. Now it's fairly easy to relate it to molarity because molarity has moles, and maybe there is a unit in there that we can cancel so that we can end up with liters. So the way I go about doing this is I say, okay, well, I need 0.072 moles of barium chloride. So I'm going to start off with what I need. 0.072 moles of barium chloride. Okay, and then I know from my definition of molarity here that a liter will give me 0.45 moles. Okay, so a liter of solution is going to give me 0.45 moles of barium chloride. Okay, so having set it up this way, my moles of barium chloride cancel, and the units I'm left with at the end of the calculation is liters of the solution. So here I'm recognizing that, well, I don't need a liter because a liter gives me way too much barium chloride. It gives me 0.45 moles. All I need is only 0.072 moles. So by setting it up this way, I'm just answering the question, how much of this solution do I need to give me 0.072 moles of barium chloride if a liter gives me 0.45 moles. So if I take a second here real quick and plug this into my calculator, I would find that I do not, in fact, need an entire liter. I only need 0.16 liters of solution. Okay, and from this, the question here asks us to express it in milliliters. So from this, we can just take this 0.16 liters and convert it into milliliters, which would just make it 160 milliliters, which corresponds to D, which is indeed the correct answer for number 7. Number 8 asks us to determine how many grams of ammonium acetate do we need in order to prepare a 300 milliliter solution of 0.5 molar ammonium acetate. So I just went ahead here and wrote down the definition of molarity so that we can use this as we insert known quantities. So we know a couple things here. We know that we want our molarity to be 0.5. Well, 0.5 molar ammonium acetate. So let's go ahead and show that. We want 0.5, and we got 3 sig figs, molar ammonium acetate. Perfect. And we also know the volume of the solution. We know that we want 300 milliliters. We got 300 milliliters, but since molarity is defined in liters, we have to express it in liters. So 300 milliliters is just going to be 0.3 liters. Okay, so the last variable here is the number of moles of ammonium acetate. That is our unknown. So in order to solve for this, I'm just going to multiply both sides of the equation by 0.3. I got 0.5 times 0.3. So what I need is 0.15 moles of ammonium acetate. Okay. So this is the number of moles I need. And if I just want to convert this into grams, then I can consult the molecular weight of the chemical, and this gives me grams. Okay, moles of ammonium acetate cancel, and now I am in grams of ammonium acetate. So if I take a second here and plug this into my calculator, I get 11.562 grams of ammonium acetate, and that rounds up to 11.6 grams, which corresponds to the answer B. And B is the correct answer for number 8. Number 9 gives us a stock solution of 18 molar nitric acid, and it asks us to determine how many milliliters of this solution we are going to need in order to prepare 2 liters of 0.5 molar nitric acid. So basically we're doing a dilution here. And anytime you're doing a dilution type problem, you're gonna use this equation here: C1V1 equals C2V2. So a lot of you have probably seen this equation in the form of M1V1 equals M2V2. These are exactly the same, except this equation is a little bit more general. So I'd like to introduce you to this equation. It's a little bit more general, where C, instead of molarity, it's concentration. So what we're saying here is that you can use any kind of concentration you want. It could be molarity, it could be ppm, ppb, and it would work as long as the concentration for C1 and the concentration for C2 are both in the same units. So that's going to be really important. They've got to be in the same units. But units like parts per million and parts per billion, ppm and ppb, perhaps you heard of them, they're often used in water quality testing, where you've got people doing drinking water and pool water testing, those kinds of things. They'll often use ppm and ppb. And volume could be also any kind of volume unit you want. It doesn't have to be liters, it could be milliliters, cups, ounces, anything. You're doing something in the kitchen, you could use this equation. So I just wanted to introduce you to the wonderful versatility of this equation, where it's not limited to molarity in liters. It's actually very applicable to any number of units, just as long as you keep in mind that the concentration units have to be the same, and also the volume units have to be the same. And then the sky's the limit. So here, in this case, we've got it kind of easy. We've got molarity in liters. So we have here, is I went ahead and assigned these to their appropriate variables. Typically, when we've got this equation, we start out with C1, V1. This is our stock solution. And then C2 and V2 are referring to the diluted solution. So I went ahead and made C1 18 molar, so that's the molarity of the stock solution, and C2 is 0.5 molar, and then V2 is 2 liters for the diluted solution. And what we're looking for here is, what is our V1? So V1 is going to be right there. What I like to do for a problem like this, if I've got an equation and I know all of my variables but one of them, is I like to just go ahead and solve for that one variable I don't know algebraically, and then I'll plug all the numbers in at the end. So I'm just going to divide both sides by C1, and I get V1 equals C2 V2 over C1. So you notice now why it's important that the units are the same, because the units are eventually going to cancel for the concentration, and we're going to be left in units of volume, which is what we want. So let's go ahead and plug all of this in here. So C2 is 0.5 molar, and V2 is 2 liters. And we're going to divide all of that by C1 here. And C1, if you remember, was 18 molar. That was for the stock. Molarities cancel. Very important. And now we're left in the units of liters. So if we do this, we would find that we need a volume, V1, of 0.0556 liters. And then the last thing to do, of course, is to take this and convert it into milliliters. So this is just going to be 55.6 milliliters. And that is going to correspond to A. So A is the correct answer for number 9. And then lastly, for number 10, we're given that blood contains 90 milligrams of glucose in every 100 milliliters of blood. So let's relate this to the molarity equation, because we're asked to determine what the molarity of glucose is. And what we want to figure out is how many moles of glucose there are in a liter of blood. So in order to figure out what molarity is, these are the two quantities that we need to determine: moles of glucose, liters of blood. So let me just go ahead and start off with the liters of blood, because that's going to be really easy. We know that we've got 100 milliliters of blood, so this is just 0.1 liters of blood. So that's what's going to go in here. But the moles of glucose is going to require a little bit of calculation, but not a big deal. So let me start off by saying that 90 milligrams of glucose we can convert into grams, because then we can use the molar mass of glucose to get us into moles. I'm just sort of foreshadowing what I'm going to do here, showing why I'm doing this. So I'm going to convert this into grams. So milligrams cancel, and I'm now in grams of glucose. So now I'm in grams of glucose, and to go into moles of glucose, I got 1 mole of glucose weighing 180.16 grams. So grams cancel, and now my units are in moles of glucose. So if I do this, I've got 4.99 times 10 to the negative fourth moles of glucose. And what's the volume? Well, the volume is just 0.1 liters. So I've got moles of glucose, and I've got liters of blood. And so to determine the molarity, I'm just going to plug those in. And I'm going to go like this. 4.99 times 10 to the negative fourth moles of glucose per 0.1 liters of blood. And that gives me, it rounds up to approximately 5.0 times 10 to the negative third molar glucose. Alright? So that would be B. So B is the correct answer for number 10. And there we go. That was quiz number 7.